Welcome to the first lecture of Module 10. Today we're going to be quantizing light and showing how the harmonic oscillator is used in the description of light in quantum mechanics. So we're going to start off with a summary of the classical theory of light that we worked out in last class. There we calculated the electric field and we calculated the magnetic field. For the electric field, we have a sum over the different modes. We have a polarization vector. We have an amplitude that is time dependent of each mode. And then we had a spatial profile, e to the I KL dot r, because it's a plane wave. And then we added the complex conjugate of that. The wave vector KL is quantized using a box with periodic boundary conditions. And we found that then the KL can be written as 2 pi over the length of the box, big L, times 3 integers as a vector, nx, ny, and nz. And then the magnetic field looks just like the electric field, except the vector that's out in front is the wave vector crossed into the polarization divided by the frequency, omega L. We also found that the energy could be written in the following form: 2 epsilon naught times the volume times the sum over all modes of the modulus squared of the amplitudes of each mode evaluated at time t equals 0. The energy is a constant of the system and does not change as a function of time. We then defined the single quantum amplitude for a photon as the square root of h bar omega L over 2 epsilon naught times the volume, the quantization volume. And then we defined that amplitude in terms of that single quantum amplitude with an I and with a function that we called alpha L of t being a potentially complex number. Now, that alpha L of t can be used to express the energy, and we find that it goes as a sum over the modes h bar omega L modulus of alpha L of t squared. Now, we also had operators that we called quadrature parameters, and those objects were called QL of t and PL of t. They had a square root of h bar over 2 that multiplied them, and then they were the real or the imaginary part of these amplitudes alpha L of t. So we have an alpha L of t plus alpha L star of t, or we have an alpha L of t minus alpha L star of t divided by I. In terms of those objects, we could then write the energy as the sum over L omega L over 2 QL squared of t plus PL squared of t. You see that when we change from the modulus of alpha L squared by looking at taking a QL squared plus a PL squared, we have a factor of h bar that cancels from that, and it then just gets written in terms of the omega L over 2. And there's also a factor of 1 over 2 that enters as well. All right, now we're ready to quantize. What we're going to do is we're going to elevate those objects, the quadrature parameters QL and PL, into operators that we're going to call QL hat and PL hat. And we're going to give them the commutator QL hat PL hat is equal to IH bar delta LL prime. And now you can see the reason why we were calling them QL and PL, because they actually are acting like a position and momentum in this abstract quantization that we're using for light. We then define ladder operators the same way that as we did before, 1 over square root of 2 h bar QL plus IPL, and 1 over square root of 2 h bar QL minus IPL. And this is the same form as we had for the Dirac operators, but the constant in front is just slightly different from the way that we described raising and lowering operators for the simple harmonic oscillator in the Dirac form. We're also going to elevate the energy to becoming the Hamiltonian operator. So when we write it in terms of the quadrature operators, it becomes sum over the modes, omega L over 2, QL squared plus PL squared, or it becomes sum over the modes h bar omega L times AL dagger AL plus a half. And now you should be able to very directly recognize that this is isomorphic to a simple harmonic oscillator. We also are interested in the electric field. Many of our measurements are going to involve looking at measurements that use the electric field. It isn't observable. We can measure the electric field, even the electric field due to a single photon. We separate that electric field into a plus and a minus piece Be careful, the plus piece is associated with the lowering operator and the minus piece is associated with the raising operator. So the electric field operator is then the sum over the modes, I times this single quantum amplitude, epsilon L of 1, times the polarization, epsilon L, times the lowering operator, AL, e to the I, KL dot R, plus a Hermitian conjugate. This is a time-independent version of the electric field. We're going to add time dependence using the Heisenberg relationship, where the time dependence goes with the operators as opposed to going with the states. And you're going to see it just involves this time evolution operator, U dagger, and U sandwiching the operator in a way that we've seen in a number of other calculations that we have done with time-dependent problems. We also work with number operator eigenstates. We're going to write those eigenstates in terms of the mode numbers, how many photons are in each mode. So I have modes numbered 1, 2, 3, 4, etc. And then the number of photons in each mode is n1, n2, n3, etc. And we just construct those in terms of a daggers raised to the proper power divided by the square root of the corresponding n factorial. So I'll have an a dagger 1 raised to the n1 divided by square root of n1 factorial, and a dagger 2 raised to the n2 divided by square root of n2 factorial, etc., all acting on the vacuum state, which is the case where I have 0 photons in each mode number. So we just represent that as 0, 0, 0, etc. Then to get the energy, we simply add up the sum over L, h bar omega L times NL plus a half, summing over all possible modes. Now here we see that there's a problem that arises, because the vacuum now has an infinite amount of energy. Because we actually have an infinite number of modes, or certainly it becomes infinite in the limit where the size of the box is made to go to infinity. For the finite box, the number of modes is not actually infinite. It'll be a finite number. But that is a huge number, sum over L, h bar omega L divided by 2. So when we're looking at energies of states, we're going to be focusing on the energy differences. Those are also always finite when I look at adding a couple of different photons in a couple of different states. So we're going to be focusing on energy differences because the vacuum energy is huge and actually diverges in the limit as the box goes to infinity. We're now going to calculate some expectation values. As I mentioned before, we're working in the Heisenberg representation. That's where I move all the time dependence onto the operators. And that means we write the operator A of t as a U dagger of t, A U of t. And if you go ahead and calculate that using the evolution operator, which, because we have a time-independent Hamiltonian, is just e to the minus I ht over h bar, you find that it just goes to AL e to the minus I omega LT. We do the same thing for the A dagger, or I can take the Hermitian conjugate of that equation, and we find that the AL dagger of t is just AL dagger e to the I omega L times t. Now we're going to look at a couple of different expectation values. We're going to be working in the expectation values for a single mode state. That is a state that has NL photons in the mode L and no other photons in anything else. Let's start by looking at the average of the electric field. When I calculate the average of the electric field, I have to plug in the definition of the electric field. That electric field has an AL term and it has an AL dagger term. And that AL term is going to change the number. If I write that NL state in terms of A dagger raised to the NLth power, that AL term is going to reduce that by one term. Or if you like, we're going to be looking at the overlap between the state NL plus 1 and the state NL. Or we're going to be looking at the overlap between the state NL and the state NL plus 1. But the states with different number operators are orthogonal to each other. So that expectation value is equal to 0. But if we look at the square of the electric field, and this is going to tell us about the fluctuations of the field, let's look at the different contributions. There are 4 terms that enter into this because I have to square the electric field. I'm going to get the square of the amplitude. I get a minus sign from the I squared. And then I have terms that go like AL squared times an exponential. I have terms that go like AL dagger, terms that go like AL dagger AL, and terms that go like AL dagger squared. The terms that go like AL dagger, those terms are going to be non-zero. The ones that go like AL dagger squared or go like AL squared, those are going to be 0 because I'm looking at the overlap between 2 states that have different particle number. And you can go ahead and calculate. You have to work with a simple commutator to make that AL dagger into AL dagger AL, then the eigenstates are, the states NL are eigenstates of the number operator. We've done this kind of calculation in the simple harmonic oscillator, and each AL dagger AL is going to give me an NL, and the commutator is going to give me a +1. So we're going to find that this is equal to 2NL plus 1. So we find 2NL plus 1 is what we get when we calculate the square of the electric field. And indeed, there are fluctuations of this electric field even in the vacuum. So when NL is equal to 0, we still find fluctuations in the electric field. And those fluctuations are very important, and they're physical and they can be measured. They're responsible for spontaneous emission. They're responsible for the Lamb shift. They're responsible for many other things. There's an effect called the Casimir effect. They're responsible for that, and so forth. So these are real fluctuations. They're called vacuum fluctuations, and they're real effects of the electric field, and we see them when we look at the problem from this quantum mechanical lens. All right, there's another set of expectation values we want to look at. They're the expectation values of the quadratures. Similar to what we saw with the expectation value of the electric field, the expectation value of the quadratures are linear in the A and A daggers, and so their expectation value is 0. When we look at the square of a quadrature, it's very similar to the electric field, but in this case we have a plus sign in there, so it's still going to give me this 2NL plus 1. The coefficient in front is different. It's an h bar over 2. We get a similar result for the expectation value of the square of the momentum quadrature. And so we can now look at an uncertainty relationship. The fluctuations in the Q quadrature and the fluctuations in the P quadrature are equal to h bar over 2 times 2NL plus 1. You should recognize that as the same kinds of fluctuations as we had for position and momentum in a simple harmonic oscillator. And indeed, the vacuum is a minimal uncertainty state. Okay, that now brings us to the end of the first lecture of Module 10.